Good afternoon. Everybody still getting their coffee fix? Yeah? Is it nap time? Yeah? At these conferences at this point, I go find a corner and I go take a nap, like Hadoop World. No. Welcome to Deep Learning on Hadoop. Let's talk about some math today, because I know you're already a little sleepy, so I'm going to go ahead and just put you on down. All right, so there's two of us today. We're tag teaming this. We're going for the title in tag team machine learning talks today. This is Adam Gibson over here. This is Adam. This will be on SlideShare later. I'm not going to talk about how wonderful and smart Adam is. You'll figure it out very, very soon. This is me. You can figure out how great I am later on. This is what I used to do. Smart grid, Hadoop, 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 blah, blah, blah. You're not here for that. Let's talk about Hadoop and deep learning. So let's break this down into four realms. I want to talk about what is deep learning, because you hear it in the media a lot right now, like on Wall Street Journal, Yahoo, what have you. A lot of articles, a lot of hype. Where does the rubber hit the road, and how can you actually use that on your Hadoop deployment today? And digging further into that, the type of deep learning we've implemented, deep belief networks, how they're implemented and how the code sits on Hadoop and Yarn, and then the results of the techniques that we've implemented that you can use today. Click. All right, come on, stragglers. Coffee wasn't that good. All right, so what is deep learning? It's not magic, and I'm going to bust some bubbles. It's not artificial intelligence. I used to be a GRA, and we would laugh about AI. We'd read Norvik's book about AI. But it's an algorithm. It's high-grade machine learning that tries to learn simple features from lower levels and build up those features and learn more complex features at higher levels of what's effectively a very exotic neural network. It reduces the problem's complexity as it moves up through the layers in the neural network. And it introduces an unsupervised component to a supervised world. It's like neural networks are traditionally, with backpropagation, they're based around the concepts of using some sort of gradient descent and calculating a loss function to update the weights. And here, there's two parts to the training, and that would be a supervised. That normal neural net learning technique would be a supervised learning technique. The interesting property that some of the researchers, such as Hinton, have introduced is an unsupervised technique, which is very interesting in places where we have a ton of unlabeled data, because unless you have just fleets of graduate students, you don't typically have a lot of labeled data, right? It's just like take these million instances and go label them for me, which takes months, years, I don't know. So supervised versus unsupervised. Unsupervised on places where there's lots of data that's unlabeled, such as a Hadoop cluster, ingesting large amounts of data, kind of becomes interesting. It also introduces some ways to do vectorization better, as opposed to you give it a more raw representation and it just says, yeah, I'm going to build your features the way I want to, as opposed to feature creation, which can be very, very delicate, involve lots of secret sauce, and quite honestly, it's kind of a black art. So what we're doing here is we're chasing nature. And given my background, if you glance at the first slide, I've always had an affinity for that when I spent a couple years in grad school studying ant algorithms, right? Because ants are really great at computers, right? No, they're not. But they are the best distributed system in nature. Bottom-up self-organization, quantitative stigmergy, things like that. So biologically inspired algorithms have always been something I really got a kick out of. Neural nets, on and off over the years, I thought they were interesting. And then when some of the later deep learning research came back up, I got more back into it. And so an interesting thing about deep learning is it's learning sparse representations of auditory signals, and this is directly from some research papers, and the filters closely represent neurons in early audio processing in mammals. So I'm not going to sit here and say it's a brain, but it has some similar properties in how it does audio processing. And that's pretty interesting. So it's biologically inspired, but it's not a brain. When applied to speech, learned representation showed a striking resemblance to the cochlear filters in the auditory cortex. There again, biologically inspired. Very interesting in how it was learned. And so Geoffrey Hinton is one top researcher. Jan LeCun, you've probably seen his, if you follow machine learning, he is a researcher at Google. Oh, no, excuse me, Facebook, my bad. Hinton's at Google, right? Yeah, okay, get them crossed. So he's one of the top guys in the game, and he has a lot of opinions about deep learning. And he's commented in one paper how acoustic modeling, deep learning has become the dominant technique. And so something that really appealed to me is as I was watching deep learning research, as you read research papers in the machine learning community, you go, who's winning the benchmark contest? Who's winning on recommendation? Who's winning on the Timet database for audio recognition? Things like that. Deep learning consistently over the past 5 years has been climbing those charts. Object recognition, object detection, semantic segmentation, things like that. Deep learning has begun, why I say it's higher grade machine learning, it's began to climb over that previous top accuracy peak, push it up farther. In machine learning, as you can see in things like cars, anybody ever work on a DARPA Grand Challenge? I did. And it was like very unglorious because I tried to do like, with OpenCV I used, we did try to do object detection in real time, and some of the techniques weren't, on some of the poor video, couldn't pick out anything, and so you can go ahead and guess what happens to a car who can't see. Don't be on the test track, all I gotta say. But whenever your machine learning techniques begin to get above certain thresholds, their value changes, and all of a sudden you have cars running around Mountain View on their own. And so that's an example of how, as we drive up accuracy, our value proposition begins to change.
There we go. Okay, so what is a deep belief network? So, we've seen the traditional multi-layer feed-forward networks, or I think we have. How many of you actually seen them? Multi-layer feed-forward? Yeah, there we go. So a couple of us have seen them. So those have been around since the 80s. We had Hinton. He created, he was essentially one of the grandfathers of neural networks. He literally he invented a lot of the baseline techniques, and he was also the innovator of what he had meant, like what Josh mentioned earlier today, being able to learn semantic representations of arbitrary pieces of data very similar to how we perceive things today, or just how we perceive things in our minds. So that being said, a deep belief network is a generative probabilistic graphical model. So what does that mean? It's a feed-forward network. It's a set of, what we'll discuss later, restricted Boltzmann machines that learn a set of features, and then you just have some sort of an output layer. That output layer is typically logistic regression, could be support vector machines. Relative to the objective function, it can do regression. It can even learn how to actually construct arbitrary pieces of data from just 10 numbers. That's called a deep autoencoder. Take notes on that later. So a deep belief network, the general idea is that you generatively learn sets of features, and then from there, you have the next layer that learns the probability distribution of the previous layer's features, etc. At the end of it, you get a latent representation of data that is actually capable of representing features better than humans can. Half of a data scientist's job is saying, what are good correlations in the data? What are the trends? What are ways I can take this data and just do something with it? This is immediately evident in computer vision. We have to do all sorts of image transforms, like a Sobel filter for edge detection, Gaussian kernels to make an image highlight features that otherwise might not be there. In natural language processing, we typically have to deal with all sorts of random features, tokens, whatever. So deep learning, deep belief networks learn these features. So I said I would explain what restricted Boltzmann machines are. So a restricted Boltzmann machine is essentially a generative model that you have an input layer, you have the visible and the hidden. The visible and the hidden clamp, they actually help each other learn. So the idea is that a restricted Boltzmann machine is actually an energy model that just says, okay, this and this, they don't match yet. They don't match yet. And what it does is it repeatedly samples it from itself in order to understand do I have a good representation of the data? The hidden learns to mirror the visible. The visible samples from the input. In this case, the major problem with restricted Boltzmann machines can be these energy functions, though, where you can only represent binary or continuous inputs. You actually have to modify the RBM such that it can handle different kinds of data. So just a little bit on a project that I kind of came on with Josh here is Deep Learning 4J. So Deep Learning 4J is essentially a distributed runtime for deep learning. Built on top of Scala, it's basically self-contained deep learning. Obviously, that's not relevant to Hadoop, though. But we can scale it with Hadoop. The idea, we can actually make deep learning a yarn app. A yarn app that can scale to arbitrary amounts of Google-level data. That Google has used deep learning at scale for years now. So the idea here was to model what would be an ideal distributed system and try to figure out what all the logistics are at runtime. In this case, it talks to any data source, sets itself up, runs some distributed calculations, and gives you just a nice lightweight model. The idea would be the same with Yarn on HDFS. So one key thing here with deep learning is everything is vectorized. In machine learning, typically what you'll do, you'll take some data, you'll turn it into what's called a feature vector. A feature vector, for those of you who don't know, is just a representation of data such that, let's just say I have housing prices, and I want to know if I'm trying to predict a housing price, I want the price, and then I want the label. So that price is a feature. So if we imagine n-dimensional, we have 100 different observations about a piece of data for a task we're trying to achieve, that's all done in vectors and matrices. So one of the things that vectorized implementations allow us to do is say, oh, here's all these examples. Let's use some nice little linear algebra, and we can solve a lot. We can actually solve all these equations and all that all at once. So in this case, GPUs are really good at that. CPU-bound tasks can be as well. They're not as fast, but CPUs don't quite. They might not be as fast, but they're a lot more accessible. So the idea is that regardless of what we do, everything's a matrix. So traditionally, deep learning toolkits have been very research-driven. There's nothing that's been easy to use. So we see that in these Python implementations. Theano, a lot of the libraries that are wrapped around that. So another one would be Torch, that's written in Lua. A lot of these systems are not meant for distributed runtimes. They're meant to run on laptops, and they run very fast. Deep learning can be very slow to train if you don't do it at scale, which is why, again, whenever Hinton talks, he's like, well, this model, it's like 98% accuracy, but it took a month to train. Who wants to wait a month? That's Hadoop. That's what we're using Hadoop for. Let's throw CPUs at it. That's what Hadoop's good at. Let's leverage that. So what are good applications of deep learning? So we've seen, as Josh mentioned earlier, there have been all record-breaking tasks that have been achieved through deep learning. MNIST is optical character recognition, taking the numbers 0 through 9, and there's 60,000 of them, and actually getting over 99% accuracy on human handwriting. Audio processing, using moving window techniques, slicing up parts of a signal. Deep learning has actually been able to identify different elements of speech in tech, within sound waves. And text and NLP, what it's capable of doing is saying, these words, these are used in similar ways. This automatic learning and unsupervised representation learning allows us to actually say, given a word, how is it used? And we can actually turn that into a vector. We can then feed that into a deep belief network and do named entity recognition. Work by Colobert and a lot of the people at Stanford, Richard Socher, actually has shown that we can actually get record-breaking NLP tasks, like sentiment analysis, for example. If you've seen that, again, like over 90% accuracy, easily. Those are traditionally really, very hard problems that we have to take a lot of time to figure out what the features are for. Deep learning handles a lot of that for us.
Yeah, so So that's some of the theory and the fundamental of what we're dealing with. And so you have really a couple levels here, but one he talked about the fundamentals of how RBMs and layers build up to deep belief networks. But how do you really execute that on Hadoop? So that's what I want to talk a little bit on the next section. And this builds on some of the prior art that I've worked on and then learned from, especially things like Valpelwabbit and some work out of Google, like Downpour SGD, Jeff Dean's work, obviously. But previously, I'd done some work with parallel linear regression. Kind of started out with logistic regression, which are general linear modeling, and parallelizing that with parameter averaging. And that's a trick that I learned from like Alex Smola out of Google, and then it's used throughout of parallel SGD work with Jeff Dean's work. And then I did an implementation of just stock neural networks, and then Adam kind of dropped out of the sky, and he said, "You're doing all your math very poorly. We should do it vectorized, and it's insanely faster." And I was kind of like, okay. And then he showed me, and I was like, okay, I'm wrong. I can admit it on stage. So, and then I packaged it in Metronome, and then this has been my developmental parallel iterative algorithm. And that's where the current, we take the core of DL4J, the concepts, the vectorized core engine, and then we've wrapped it in the iterative reduce framework to scale out with lots of workers doing shards of the data on Hadoop. And so this parameter averaging is kind of like the trick that just keeps on giving in machine learning. If you want to do linear modeling, you just lots of workers on the shards, average the parameters every so often, and eventually you get a really good answer. And you can take a look at McDonald, 2010. John Langford, incredibly well-published doctor in this space, and he's done a ton with Valpelwabbit, and Valpel's is incredibly screamingly fast. And then Jeff Dean's work is the guy I just chase all of his papers. Downpour SGD is a really interesting paper, and that's Downpour SGD paper. That's where I get the bulk of my ideas for iterative reduce, the parallel framework on Yarn, and then the parallel iterative algorithms on top of that. So what does that look like? Today, we're over the past couple years, who used Hadoop before 2012? Anybody? Yeah. So it's MapReduce. That was your bell cow, and you just shoehorn things into MapReduce, and then I have this kind of theory. I have this theory, and it says that as the amount of data in your organization approaches 100% in Hadoop in HDFS, the amount of in-place analytics will approach 100% in Hadoop as well. And Yarn has driven that, has all the wonderful work that's poured into that. And I call this, by the way, Patterson's Law, because Patterson's theorem does not sound nearly as good. Anyway, MapReduce looked about like this, and parallel iterative looks about like this. The trick is, with MapReduce, they can look very similar. Every so often you hit a boundary condition in a BSP-style processing graph. You really want those workers to stay alive, because MapReduce setup costs are like 30 seconds. Well, if you do 1,000 passes over a data set, it's like 30,000 seconds, which ends up being what, like, I don't know. It ends up being like 8 hours, I think, or something like that, of just setup costs. And you just really want to get those passes over. So if your workers stay resident, like they do in iterative reduce in Yarn, you can change the mechanics of how your parallel framework goes. And you can see more about that in some of my previous talks. And so this is what it ends up looking like. A serial online algorithm has training data, looks at example, updates the model, and then looks at the next example. And here you want each worker to sit on top of a shard of the data and have its own copy of the model. And every so often you want to have average it together with parameter averaging in a global model. Those splits line up well to HDFS blocks, right? Move the worker onto the block like a map task, but it's not a map task. It's a specialized iterative reduce worker on Yarn. There you have it. Yarn is important, though. And I think there's a lot of distributed systems talk out there these days, and Yarn solves some problems. It's complex to write to, and that's why we wrote a layer under our algorithms called iterative reduce. I think sometimes people think, oh, we're going to use Yarn. Well, typically you're going to use a fair scheduler to manage how apps use resources. But when you have something, you have isolation between applications, and everybody can share the cluster nicely, that helps. And being a first-class Yarn citizen is important. So you can mix it in with a Tez job or a MapReduce job or an Impala job, whatever your distro is, and make workflows out of it. So being on top of Yarn is important here. And they want these tools to share resources nicely. So like Adam talked before, and we talked about there's an unsupervised component to this, and then there's a supervised component to this. And the two phases are called pre-train in literature, and then fine-tune. Pre-train is when we take unlabeled data, and we run it through those RBMs with no labels, and they just reconstruct the data over and over again through each layer feeding up. And then they have basically an overall general structure of the data. And then we give it some labeled data, and we say, you have ideas. Now we're going to tell you what those ideas are, and we're going to fine-tune the model so that whenever you see this idea, you slap this label on it. And it's an interesting combination of unsupervised and supervised learning. And each phase can do, we might want to do like 10 passes over the data set of pre-train, and then only 1 pass of fine-tune, or maybe vice versa. And that's configurable in the tools. And every so often, we average the entire network graph at the master. So we send the RBMs, and then the whole feed-forward network and the logistic regression output layer all to the master, average them all together, send the global message back, network back all to the workers, and they continue on whatever pass in pre-train or fine-tune they're in. So something we're experimenting with is I feel, my gut says that Hadoop having a ton of data you're ingesting with like Flume and Kafka and things like that, I keep thinking, I'm like, this tool is going to be interesting throwing a lot more pre-train time at this data because I don't want to label it all. And if I can get away with labeling just a little bit, I can data mine a whole lot more data and get much better models. And so that's an area that we're exploring further as we work. So I'm going to let Adam talk about results we found now.
So as I mentioned before, deep learning actually has done record-breaking things. But what about, what have we done ourselves, though, right? So you want to see, you might want to see something from us. So from results, for iterative reduce, one thing I've done, which was fun, I actually set up a 28-node cluster on Amazon, I believe 30 core machines. And I ran actually all of MNIST, 10 minutes. Hinton, hours. The difference is not only that much faster training, also built-in parameter averaging for the results gives you automatic regularization. So what is regularization? Just for those of you who aren't familiar with it, the general idea is that a neural net learns features and it overfits. What you do to counterbalance that, and so the model can generalize better, is this idea of regularization. Regularization happens automatically via parameter averaging. So what else we've done is we've also added this idea of ADAGRAD, adaptive learning rates, feature-wise learning rates. So it says if this feature learns too fast, slow it down. ADAGRAD is a way of saying slow down the learning, speed up the learning, depending on the parameter that is in play. So we're still experimenting with whether we want to average ADAGRAD or what we want to do. The key point here is it's adaptive and it's more robust. So what are some of the scale-up metrics we need to play with? So if we think about Hadoop, if we think about any distributed system, we need to think about what is our batch size. What are in any intro to Hadoop, you'll hear about input splits and all sorts of random optimization metrics. So what we need to think about is how many records do we want to average on? So the smaller the idea is that the smaller the batch size, usually 10 to 100, depending on your data set, you're going to want, you usually want it smaller if possible. The idea to counterbalance this is to say, if I have 100 workers, if I train on 100 at a time, it'll train faster. If I train on a smaller amount, it actually might be more accurate. It really depends. The other thing we have to think about here is message passing. So this is just saying train on this bit of data, train on this bit of data. In a distributed system, this gets chaotic, adds a lot of overhead. So we need to counterbalance that and think about when we're deploying this, what do we want to train on? This is all configurable via properties files. It's all right in there. You call the yarn jar, it figures out, oh, here's my configuration. Use that to tune what you're doing. So, if we get into the command line here, so all you need to do is literally just think about how we normally run a Hadoop app. Java jar, my gigantic jar file, and my configuration. From there, all you need to do is worry about training your model and all the other fun stuff that goes with that. So what are some of the things we've seen? So this is an example of handwriting renders. So handwriting is from MNIST, as I had mentioned earlier. This is actually each neuron being rendered by a deep belief network or by a restricted Boltzmann machine. The idea is that it learns how to, each neuron actually learns how to draw a 2, a 3, a 9, a 7. And then from there, it uses the images themselves and its internal representation as features to learn how do I recognize what a 1 is. And it does this, again, by repeatedly sampling the data. And again, we've had record-breaking results on MNIST. So at the very minimum, the papers, it works. As crazy as it sounds. Not human-done features? What's going on here? It works. So I don't know how many of you guys have heard of DeepFace by chance. This is the DeepFace data set, labeled faces in the wild. Again, same results. So why am I showing you face renders and all this other stuff over and over again? The reason here is to visualize how a neural network learns. A neural network learns by learning how to redraw the things you show it. These reconstructions will be different for different data sets you show it. You can actually also use this in debugging. The general idea is that the cloudier it is, the worse it is. Or maybe it's just too early in the training. There's all sorts of techniques you can use. The idea is to understand, is the network learning what I want it to? We can also do this with words and all other sorts of things, but I wouldn't recommend the renders unless you were doing computer vision. This is, again, just to visualize a concept. So what did DeepFace do? DeepFace actually beat human accuracy on labeled faces. 98.5% accuracy. The last result was around 97.5. It actually is marginally better than humans. So again, we've seen this with text, audio, anything you can think of. Now, just so you're not asleep here, what about cat photos? The internet loves cats. So what if we, if you guys remember Andrew Ng's research, he actually taught a gigantic neural network to learn what a cat is. So it actually output its general representation of a cat. Again, same idea. We showed it some cats. It's like, recognize all these different kinds of cats. Now we actually can build a cat classifier. So the general idea, in closing here, is that we have this, these three or four layers, stacked RBMs. They learn features, and then relative to your output layer, they do some task. Regression, so you can predict. All the things you could do in neural networks can now be done in a more automatic fashion. So what are some future directions? What else could we do? So Amazon actually allows you to do GPU instances now. So we want, the researchers are harping on GPUs. So what if, so one thing we want to do is we want to actually add GPU processing to this. The other thing is to make this a little more turnkey, vectorization tooling. If we remember, there's all sorts of vectorization things that we need to do in order to feed things into a neural network. A neural network speaks matrices. Linear, all sorts of machine learning algorithms speak matrices. So better vectorization tools for different kinds of data, like sound, text, images, whatever you might want to do, video. We want to vectorize those in appropriate ways. So better tooling. And also Yarn. So one key thing here is that Yarn currently uses Mahout matrices, which Java matrices are slow. We want native. Luckily, this is changing. One of my constraints with Hadoop was, well, why do we have Java matrices? Now we're going to be moving over to JBLOS. JBLOS is basically Java with native matrices. So you get all the nice little operations of matrices, like in the Java language, without worrying about, oh, this is native or what's going on here. You can just say, install JBLOS, you're done. So just some references. Obviously we're standing on the shoulders of giants. That's how you further research. So one thing is a fast learning algorithm for deep belief nets. The algorithm, the original pre-trained part, the auto learning came from Hinton in 2006. That kind of spurred the revolution into what we see now. Large-scale distributed deep neural networks, this was Dean, and also debugging. So we mentioned neural nets are a black box. They can be hard to debug. There are, luckily, all sorts of techniques and visualizations, histograms, plots, that we can actually do to actually show what is going on in the learning and allow us to make smart decisions. the typical workflow with this is you run an iteration, you train it on a bit of data, and then you see how it reacts. And then you can usually, within 1 or 2 iterations, figure out what it's doing without a lot of, oh, let me just wait 8 hours and then see if the results are good. You can actually react accordingly.
Questions?
Let me ask more specific about, did you implement check-ins algorithm, or do you have
Parts of them.
Parts of it.
Parts of it.
what about the scale of the experiments, like the number of parameters for the model? Or
So MNIST is what, 1 million for parameters?
Something like that, yeah.
Okay, I'm sorry. How many parameters are we looking at? So typically, I think if you look at the Google research, they get up into the hundreds, millions, and billions of parameters. So far, the data sets that we have, if we've built up the system, are only in the millions. But there's no reason you can't try bigger. It's just like when you're debugging, I don't want to wait for, if you're only debugging on like 1 machine or 3 machines or in the simulator, I don't want to wait for 3 days to figure out if whether or not my message passing was working. So in the millions is where we're at right now, but there are some constraints once you go up into the hundreds of millions. It ends up being you need a parameter server to begin sharding the parameters out. So if you look at his research, they use a parameter server, which Google recently open sourced. We're just not there yet to need it, but yeah, it's still modeled after some of the smaller parameters. But in the millions of parameters, not a lot of people have needs for millions of parameters today. But the scale architecture and the lineage is there to go up.
So in Deal4j, in distributed Deal4j, is a parameter server?
Yeah, so it's literally iterative reduce.
So are you using Hazelcast as well?
Yes. Yeah, I use Zookeeper for the configuration and Hazelcast for the distributed lock and everything that goes into that.
So to be clear, I want to make there's a DL4J like core like math libraries, and then we've wrapped that in different execution places. So you can run it on your laptop, you can run it on Akka, you can run it on Yarn, but each one has like different, like it's run differently, but it's ported to different places.
What's a parameter server for Yarn?
Today there's no parameter server for Yarn because we don't have 200 million parameters in a network yet. It's just not.
So is there any efficiency there? Is there any trade-off there between the Yarn version and the Akka version?
So the Akka version, I would say, isn't as robust. I mean, Hadoop was built by people way smarter than us, probably the sum of people in this room. So I would counter that, the Akka version is great and is more meant for self-contained deployments and smaller amounts of data. It can scale, and I have scaled it out to, like I said, 20 nodes on Amazon and all other sorts of crazy stuff like that. But if you want, this is a distributed runtime that I mainly wrote just to say this is self-contained. You can run it. It's a lot easier to set up than I would say Hadoop is.
Yeah, so it's like it's kind of like it's like a core engine in a different deployment mode. So if you want to just run a quick distributed system, that would be a great way. If you have a Hadoop cluster and you want to run deep learning on your data in place, you run the Yarn version. But it's the same mathematical model either way.
Just one more follow-up. Just kind of a general question about Deal4j. Have you tried to do semantic hashing at all?
Yes, so I actually have if you look at the source code, there's actually a deep autoencoder in there. I do semantic hashing. And I have had good results with it. Both with word to vec vectors. So I've done document search. I've also done computer vision with it. Could you repeat the question?
Do you have any good method to visualize the features?
Oh, yes. So besides the filters, we also have histograms for the weights as well as plotting the activations. And all you do is debug it via literally colors.
Yeah.
So how dark is it? You can see like literally over time how well it trains.
Yeah, I mean, I actually had those renders, but unless you're like a deep learning person, like showing people activation grids is on screen is kind of like crickets chirp. So like we can show them to. I have them on my laptop. Also the reconstructions, if you watch the number 1 start out as just fuzz, and then it begins to reconstruct 1. We have those too, and you can run a unit test and generate them. So it's the codes in there to execute. It's built in. front.
So for somebody who's like unfamiliar with all of this stuff, what's a good way to get started, getting your feet wet with it, to get it stood up on a Hadoop cluster and trying some stuff out?
Do you have CDH4.6? Just build the yarn jars and use like what I would do. And I have a demo data set in it. So instead of you needing a big cluster, just take like 2 labels of MNest. So it's only like a 1 and a 0, and just like 20 samples, and run it and just watch it learn and go, okay, A or B. You know, it's a 1 or a 0 based off a whole like 20 images. And that's a great way just to say, oh, this works. And that's built into the unit test. You can run that simulated run too. And we can help you get that running. You know, the instructions are on the wiki. Anybody else? No?
Lots of those. Come see me after.
Yeah, Deep Learning 4J has got a really great wiki that just goes into a lot of literature and then a lot of plain spoken kind of, this is where the code and this is kind of the history behind it, and explains the different chunks of it if you want to go deep. Or if you just want to run the command line, that's one thing. You can also have a lot of literature and a lot of links in there for you to understand what's going on if you have a couple spare months on your to go read stuff.
Oh, so we actually have, so that's the thing. I actually, in Deep Learning 4J, have recursive neural tensor networks, the Socher nets, as well as the convolutional multi-layer network and convolutional restricted Boltz machines. So the last one I need to actually make is a recurrent net, but right now I'm working on refining those right now.
Yeah, there's a lot of exotic networks out there at this point. We're in the special snowflake field of neural networks. They all get these really exotic kind of properties to them, and there's a lot to. Ming?
I have a question because neural networks are support vector machines. They are like black boxes in many ways. You can do the visualizing, plotting, all that, but how would you apply that in the heavily regulated industry? Like you have to explain to the insurance commissioner saying, this is how you modeled and that's why you're setting your rate at blah, blah, blah. So that would be a big limitation. Is there any work done in that way to be able to sell your neural network models a bit easier?
So Ming's question is, how do you typically, like if you have a logistic regression model, you can go look at where the weights were and go, hey, like age and square footage of the house correlate really well to sell price, right? And you can explain that model. Well, with a million parameters, it's just in a nonlinear function, you can't make any sense of it. So how do you go to like actuaries in the insurance space and go, hey, this is what this model means? You don't. I think, what is it, Leo Breiman's paper where he talks about there's two worlds, and then one world you just have to build really good models that have low error rates. And then you go, it works, it's a black box. And the insurance industry will decide, different types of industries will be much slower to adopt them. And that's a tough part about using this, because they want something they can explain. If you go, it's this magic neural nets, it usually doesn't fly in certain industries. So there's some realistic places where you can and cannot apply these things. Back?
So we've used labeled faces in the wild. I've actually done sentiment analysis with tweets. I've done a lot with deep autoencoders and actually compressing just cat, I just did the cat faces, for example. I have a lot of proprietary customer data sets as well that I've done fraud detection with. I've done all sorts of regression. I've actually done regression and prediction with them. So we've been using these for a while.
So yeah, I mean, we've worked in this system for 6 months building components and unit testing at every level to get it all to work together. Another one that I use a lot of UCI data sets just because they're well known. One of them is like COV type. That's something I got from like Sean Owen, who's well known in the space, and he said, yeah, that's always the data set that I use. So it gets like amazing percentage on COV type, COV, TYPE, and UCI's repository.
And we've actually, and obviously, like, we've done a lot of, like, Iris. We're actually going to be working with the Timit data set soon, so, audio.
Yeah. Audio, I think, is interesting because deep leaf networks are pushing that high score up farther. And then that, Hadoop, I've been doing Hadoop since 2009, and it's been very log-based, ETL-based, and then we begin to transition into different types of workloads. And I think you're going to see over the next couple of years, it's going to ingest audio, video, and general sensor. And I used to do general sensor on it. And so audio and video, deep leaf networks really work well on those, and that's an interesting kind of futurist trend. So we're trying to meet that trend a bit. But it works great on text, too.
Apache. Both of them are Apache.
Yep, GitHub, Apache. There's nothing, it's right there. Take it, do what you want, You want support? Come get a business card. We'll help you out, for hourly rate. But, it's classic kind of hoop. Getting close to time. What else we got? Thanks, guys. Appreciate it.